On January 5, 1943, 4 Japanese dive bombers attacked a U.S. Navy task force operating off Guadalcanal. The engagement should have been routine. The old Aichi D-3A Val bombers made their runs, scored 1 hit on a New Zealand cruiser, then turned to escape. Anti-aircraft gunners aboard the cruiser USS Helena fired a cursory parting shot at the departing aircraft, 2 salvos from the ship's 5-inch guns. One of the Japanese bombers exploded in midair and fell into the sea. The odd thing was that none of Helena's shells had hit it directly. They'd exploded nearby, close enough that shrapnel tore through the aircraft's structure and sent it tumbling from the sky. The Japanese pilots who survived didn't understand what had happened. Neither did most of Helena's crew. But a small group of officers aboard the cruiser knew they'd just witnessed history. The first enemy aircraft deliberately destroyed by a weapon that would change aerial warfare forever. The shells Helena fired that day contained a secret so closely guarded that its existence was classified above virtually everything except the Manhattan Project. Inside each shell's nose was a miniature radio transmitter and receiver, a tiny radar set that sensed when the shell passed close to a target and detonated automatically. No direct hit required. No timer to set. Just proximity to the enemy and death. It was called the proximity fuse, though the Navy deceptively referred to it as the VT, or variable time fuse, to disguise its true nature. And over the next 2.5 years, this device, barely larger than a fist, containing 130 miniaturized electronic components and 5 glass vacuum tubes, would shoot down hundreds of Japanese aircraft, devastate German ground troops caught in the open during the Battle of the Bulge, turn London's anti-aircraft defenses into an impenetrable barrier against V-1 flying bombs, and force a complete revision of tactical warfare. General George Patton would credit it with winning the Battle of the Bulge. Navy commanders would call it indispensable to victory in the Pacific. And Hitler never saw it coming. This is the story of the proximity fuse, the billion-dollar secret that turned near misses into kills, that made obsolete decades of anti-aircraft doctrine, and that demonstrated how a small technological breakthrough could multiply combat effectiveness beyond anything imagined possible. Real quick, please like and subscribe to help our channel grow. Now back to the story. The problem that couldn't be solved. Before the proximity fuse, shooting down aircraft with anti-aircraft artillery was an exercise in futility verging on desperation. The mathematics were brutal and unforgiving. An aircraft moving at 300 miles per hour covers 440 feet per second. An anti-aircraft shell fired at 20,000 feet altitude takes roughly 15 to 20 seconds to reach that height, during which time the aircraft has moved nearly 2 miles from where it was when the gun fired. Gunners had to predict where the aircraft would be when the shell arrived, set a timer on the fuse to detonate at the calculated altitude, and hope their prediction was accurate. It almost never was. Aircraft maneuvered unpredictably. Winds aloft affected shell trajectories. Fuse timing mechanisms weren't perfectly consistent. Fire control calculations were approximations rather than precise measurements. The result was that anti-aircraft guns fired thousands of shells to achieve a single kill. During the Battle of Britain, it took an average of 20,000 rounds of anti-aircraft ammunition to down 1 German aircraft. Some estimates suggested that ratio climbed as high as 50,000 rounds per kill during sustained campaigns. The 2 types of fuses available in 1940 were both inadequate. Contact fuses only exploded when they physically struck the target, turning anti-aircraft gunnery into the equivalent of trying to hit a flying baseball with another baseball. The odds of direct impact at combat ranges were essentially 0. Time fuses which detonated after a preset delay, were better, but still required predicting the exact moment when shell and aircraft would occupy the same point in three-dimensional space. Get the timing wrong by half a second, easy to do when you're calculating trajectories for a shell fired at a maneuvering target thousands of feet away. And your shell explodes harmlessly 200 feet from the aircraft. The British and Americans both understood that a proximity fuse, one that detected the target and detonated automatically when close enough, would revolutionize anti-aircraft warfare. The concept wasn't new. Various nations had experimented with proximity fuses using optical sensors, acoustic triggers, magnetic fields, and other methods since the 1930s. But every design faced the same insurmountable problem. The components were too large, too fragile, or too unreliable to survive being fired from a gun. Consider what a proximity fuse had to endure. When a 5-inch gun fires, the shell accelerates from 0 to 2,800 feet per second in about 16 feet, the length of the gun barrel. That acceleration generates forces exceeding 20,000 times gravity. For comparison, astronauts during launch experience roughly 3 to 4 Gs. The proximity fuse had to contain delicate vacuum tubes, radio circuitry, batteries, and explosive charges, all of which had to survive forces that would instantly destroy any normal electronic device. Then the shell spun at up to 30,000 revolutions per minute due to the rifling in the gun barrel, creating centrifugal forces that added to the stress. The fuse had to function reliably after being subjected to these conditions, in any weather, at any temperature, sometimes after months in storage. Nobody thought it could be done. The British Teasard mission, which traveled to the United States in September 1940 to share military technology, brought proximity fuse research with them. But the British scientists were pessimistic. They'd concluded that creating a proximity fuse rugged enough for artillery shells was technically impossible during World War II. Bombs and rockets, maybe. Those experienced far gentler acceleration and didn't spin. But artillery shells. The physics seemed insurmountable. The Americans decided to try anyway. The scientists who shrank the impossible. In 1940, the National Defense Research Committee assigned the proximity fuse problem to Section T, a research group led by Dr. Merle Tuve at the Carnegie Institution and Johns Hopkins University's Applied Physics Laboratory. Tuve was a physicist who'd worked on nuclear fission research, and he brought to the proximity fuse project the same systematic, problem-solving approach that characterized modern physics. The challenge was daunting. Miniaturize a radar system to fit inside a shell's nose, make it survive gun firing, and ensure it worked reliably in combat conditions. The team started by identifying the fundamental requirements. The fuse needed to transmit radio signals continuously, receive the reflections from nearby objects, and detonate when the reflected signal indicated proximity to a target. This required a transmitter, receiver, amplifier, power source, and firing circuit. Essentially, a complete radio set, shrunk to fit in a space about 3 inches in diameter and 5 inches long. And every component had to be ruggedized beyond anything previously achieved in electronics. The key breakthrough involved miniaturizing vacuum tubes. Pre-war vacuum tubes were relatively large, fragile glass devices designed for radios and other stationary applications. They couldn't survive the shock of gun firing. The glass would shatter. The filaments would break. The carefully aligned internal elements would be destroyed by acceleration forces. The team needed tubes 1/10 the size of standard tubes. with structural strength far exceeding anything commercially available. They found an unlikely solution in hearing aid tubes. Western Electric and RCA had developed miniature tubes for hearing aids in the late 1930s, tiny devices about the size of a thimble. These weren't designed for military applications, but they provided a starting point. Section T worked with Sylvania Electric Products to modify these tubes, strengthening the internal structures, improving the mounting systems, and testing them under conditions that simulated gun firing. The development process was iterative and frustrating. Design a tube, test it, watch it fail, identify the failure mode, redesign, test again. Thousands of tubes were destroyed during development before they achieved a design that could reliably survive being fired. The radio circuitry presented equal challenges. Standard circuit boards and wiring methods couldn't survive the acceleration and vibration. The team developed new construction techniques using shock-resistant mounting, potting components in protective compounds, and designing circuits that functioned despite the extreme conditions. Every connection had to be mechanically secure and electrically reliable. After experiencing forces that would tear apart conventional electronics, power requirements were solved through a clever mechanism. The shell's spin activated a small generator using centrifugal force. The rotation that was part of the problem became part of the solution, generating electricity to power the fuse during flight. A backup battery provided initial power and ensured operation if the generator failed. The entire power system had to fit inside the fuse housing alongside all the other components. The firing circuit was equally sophisticated. The fuse transmitted radio signals at roughly 180 to 220 megahertz and listened for reflections. When the reflected signal reached a certain strength, indicating the shell was close to a target, the circuit triggered a small detonator that set off the main explosive charge. The threshold was adjustable during manufacturing to control burst distance. 30 feet for anti-aircraft use, 10 to 70 feet for ground targets, depending on the desired effect. This required precisely calibrated amplifiers and discriminator circuits that could function reliably despite temperature variations, humidity, and the mechanical stress of flight. By August 1942, the team had a working design ready for testing. The USS Cleveland conducted live fire tests in Chesapeake Bay using remote-controlled drone aircraft as targets. The test was scheduled for 2 days, but it ended after the first day when proximity-fused shells destroyed all available drones with just 4 bursts of fire. The success rate was unprecedented, far exceeding anything achieved with time-fused shells. The Navy immediately authorized mass production. The manufacturing miracle. Producing proximity fuses in the quantities needed for war required transforming an experimental laboratory device into a mass-manufactured product built by workers who'd never seen sophisticated electronics. The challenge wasn't just technical. It was organizational, industrial, and human. Creating millions of complex electronic devices to exacting specifications while maintaining absolute secrecy tested American manufacturing capability in ways that few other wartime programs did. Sylvania Electric Products received the primary contract for tube production. Their facilities in Pennsylvania, Massachusetts, and elsewhere were retooled specifically for miniature vacuum tube manufacturing. The production process was entirely manual. Women workers, recruited specifically for their small hands and attention to detail, assembled the tiny tubes by hand under magnification. Each tube contained dozens of precisely aligned internal elements, filaments, grids, plates, that had to be positioned within tolerances measured in thousandths of an inch. The work was tedious, eye-straining, and absolutely critical. A single misaligned element could cause a tube to fail, and a failed tube meant a fuse that wouldn't function, potentially costing lives. Fuse assembly was distributed across multiple facilities. General Electric plants in Schenectady, New York, and Bridgeport, Connecticut assembled the complete fuses. Crosley Corporation in Cincinnati produced fuses. RCA, Eastman Kodak, and other companies joined the production network. Each facility received components from suppliers, tubes from Sylvania, capacitors from one manufacturer, resistors from another, cases from a third, and assembled them into finished fuses following procedures developed by Section T. The distributed production system provided redundancy and increased total output, but it complicated quality control and required extensive coordination. Security was intense. Workers weren't told what they were building. They were searched entering and leaving facilities. Personal items, including purses, were prohibited. Even local police and fire departments couldn't enter without special authorization. The women assembling fuses in Ipswich, Massachusetts, worked under conditions of secrecy that bordered on paranoid. But the secrecy was necessary. If Germany or Japan discovered the proximity fuse's existence and developed countermeasures or copied the technology, the advantage would evaporate. The entire program operated under classification levels exceeded only by the Manhattan Project. Quality control was equally stringent. The National Bureau of Standards established a controlled testing laboratory that subjected sample fuses from each production lot to extreme tests. Temperature cycling from below freezing to well above operational temperatures, humidity tests simulating tropical conditions, shock tests using devices that replicated gun firing forces. Fuses that failed any test caused their entire production lot to be rejected and investigated for systematic problems. This rigorous testing caught manufacturing defects before they reached combat, but it also slowed production and increased costs. By late 1942, production was delivering about 500 fuses daily. By the end of 1943, production reached 40,000 per day. By war's end in 1945, factories were producing 70,000 fuses daily, nearly 2 million per month. The total program cost exceeded $1 billion in 1940s dollars, roughly $15 billion in modern terms, making it one of the most expensive weapon development programs of the war. More than 22 million proximity fuses were produced between 1942 and 1945, each containing about 130 individual components assembled with precision that pushed contemporary manufacturing to its limits. The industrial achievement rivaled the technical breakthrough. Transforming a laboratory prototype into millions of battlefield-ready devices in under 3 years required solving problems that had never been attempted before. American industry's ability to manufacture complex electronics at scale proved as decisive as the technology itself. Germany and Japan both researched proximity fuses. Germany reportedly developed 30 to 50 different designs, but neither achieved mass production. They lacked the industrial capacity, the specialized components, and the manufacturing expertise that American companies had developed. The proximity fuse wasn't just a technical advantage. It was an industrial advantage that enemies couldn't replicate even when they understood the concept. Pacific Proving Ground. The proximity fuse entered combat in the Pacific because that theater offered the safest testing conditions. Shells fired over water wouldn't fall into enemy hands if they malfunctioned. Japan was considered less likely than Germany to develop effective countermeasures, even if they captured an intact fuse. and the Navy needed every advantage against Japanese air attacks that were growing increasingly skilled and desperate. Helena's success off Guadalcanal in January 1943 was just the beginning. Throughout 1943, proximity-fused shells proved devastatingly effective against Japanese aircraft. The statistics were remarkable and unambiguous. In 1943, naval guns fired 36,370 anti-aircraft rounds, of which only 25% used proximity fuses. Yet those proximity-fused shells accounted for 51% of all kills. The average rounds per kill dropped from over 500 for time-fused shells to approximately 155 for proximity-fused shells, a threefold improvement in efficiency. At night, when visibility made time-fused fire even less effective, the kill ratio improved by 370%. The tactical implications were profound. Ships could engage aircraft at greater ranges with higher probability of kill. Small escort vessels with limited ammunition loads became far more effective. A destroyer that could previously expect to shoot down 1 or 2 attackers could now threaten 5 or 6. The increased effectiveness meant fewer aircraft reached their targets, which meant fewer ships were damaged or sunk, which meant more sailors survived. The proximity fuse was saving lives with every shell fired. Japanese pilots noticed the difference immediately. They reported encountering a new type of anti-aircraft fire that detonated near their aircraft, even when they were maneuvering violently. Some pilots believed the Americans had developed aircraft-seeking shells that somehow tracked targets. The reality was simpler, but equally effective. The proximity fuse's lethal radius was roughly 3,000 square feet compared to 60 square feet for time-fused shells. A 50-fold increase in the probability that a near miss would cause damage. The fuse proved particularly valuable against kamikaze attacks that began in late 1944. Kamikaze tactics relied on overwhelming defenses through sheer numbers and determination. If enough aircraft attacked simultaneously, some would get through regardless of losses. The proximity fuse degraded this calculus by increasing the probability that each attacking aircraft would be destroyed before reaching its target. During the Battle of Okinawa in 1945, proximity-fused anti-aircraft fire was credited with being indispensable to fleet survival. In one 90-minute engagement, the destroyers USS Hadley and USS Evans, supported by proximity-fused ammunition, destroyed dozens of attacking aircraft, far exceeding what would have been possible with time-fused shells. The Navy's embrace of the proximity fuse was total by 1945. Nearly 2/3 of all proximity fuses expended during the war were used in just 7.5 months of 1945, reflecting both increased production and the intensity of kamikaze attacks. The fuses changed anti-aircraft doctrine fundamentally. Previously, large-caliber guns required complex fire control systems that were expensive and took time to lock onto targets. Proximity fuses eliminated the need for precise range setting, allowing simpler fire control systems to be used effectively. Ships began connecting their 5-inch guns to lightweight Mk-51 directors originally designed for smaller weapons, multiplying the number of targets that could be engaged simultaneously and slashing response time. The proximity fuse didn't just make anti-aircraft fire more lethal, it made it faster and more flexible. The secret comes to Europe. While the Navy used proximity fuses extensively in the Pacific, the Army was forbidden to employ them in Europe. The Pentagon feared that duds falling into German hands would compromise the technology, either through direct copying or by allowing development of countermeasures. Germany's technical sophistication and industrial capacity made them the most dangerous potential recipient of proximity fuse secrets. The army chafed under this restriction, knowing they possessed a weapon that could save lives but couldn't use it. The restriction relaxed in June 1944, when Germany began launching V-1 flying bombs against London. The V-1s were cruise missiles, pilotless aircraft flying at 400 miles per hour, programmed to dive on London when their fuel ran out. They were terror weapons, killing thousands of civilians and threatening to make the city uninhabitable. British anti-aircraft defenses struggled against them. Time-fused shells required predicting when the V-1 would pass through the burst point, difficult against targets that flew predictable paths but moved very fast. The kill rate in June 1944 was only 17%. Churchill requested proximity fuses, and the Americans agreed. The restriction on European use was lifted for anti-aircraft guns positioned along the coast, where duds would fall into the channel and couldn't be recovered. The results were immediate and spectacular. By late August, the kill rate had climbed to 74%, some days reaching 82%. The coastal gun belt became nearly impenetrable. V-1s that survived the guns faced fighter interceptors inland. But proximity-fused anti-aircraft fire destroyed most before they penetrated far into British airspace. The fuse saved London as certainly as any weapon deployed in the war. When the port of Antwerp, critical for supplying Allied armies advancing into Germany, came under V-1 attack later in 1944, proximity fuses were rushed there by special Lancaster bomber flights authorized by Churchill personally. The fuses kept Antwerp operational despite sustained German attacks. The strategic importance was immense. Without Antwerp's supply capacity, the Allied advance would have stalled for lack of fuel, ammunition, and supplies. Proximity fuses, originally developed to shoot down aircraft, had proven equally effective against the first cruise missiles, demonstrating versatility that developers hadn't anticipated. The Bulge. Artillery reimagined. The proximity fuse's most famous ground combat employment came during the Battle of the Bulge in December 1944. The German offensive surprised Allied forces, pushing deep into Belgium and threatening to split American armies. The weather was terrible. Snow, fog, low clouds that grounded Allied aircraft and eliminated the air superiority that had become decisive on the Western Front. German troops, accustomed to being bombed constantly, moved more freely during the cloudy weather, believing they were safe from both air attack and accurate artillery fire. General Eisenhower authorized the use of proximity fuses for ground combat on December 18th, 2 days after the German offensive began. 200,000 artillery shells with VT fuses, codenamed POSIT, were rushed to frontline units. The results were catastrophic for German forces. Artillery shells exploding 20 to 50 feet above ground sprayed shrapnel downward and outward, hitting troops in foxholes and behind cover that would have protected them from ground bursts. The effect was devastating in ways that shocked even experienced German soldiers. General Patton witnessed a demonstration of proximity-fused artillery on December 16th and immediately understood its potential. He ordered the fuses kept secret until they could be employed at a critical moment. On December 24th to 25th, as German forces attempted to cross the Sauer River near Echternach, American artillery using proximity fuses caught them in the open. Patton later wrote that they'd killed 702 Germans, by actual count, in a single artillery concentration. German troops watching the attack reportedly refused to leave their bunkers during subsequent bombardments, creating discipline problems that weakened German combat effectiveness. The proximity fuse's anti-personnel effects exceeded anything traditional artillery could achieve. Time-fused airburst fire had been standard artillery doctrine for decades, but it required accurate observation and precise fuse setting. In the Bulge's terrible weather, observation was often impossible. Proximity fuses worked regardless of visibility. Set the shell to burst at the desired height, fire, and the fuse handled the rest automatically. German soldiers felt safe from artillery during bad weather because they assumed gunners couldn't see them. The proximity fuse eliminated that assumption. Artillery became equally deadly in any weather, at any time, against any target in the open. Patton's assessment was characteristically blunt and accurate. The new shell with the funny fuse is devastating. I think that when all armies get this shell, we will have to devise some new method of warfare. I'm glad that you all thought of it first. He later credited the proximity fuse with saving Liège and stated that its use required revision of land warfare tactics. This wasn't hyperbole. The proximity fuse genuinely changed how artillery functioned, transforming it from an area weapon that suppressed enemies through volume of fire into a precision anti-personnel weapon that killed exposed troops with terrifying efficiency. The weapon that changed everything. By war's end, proximity fuses had transformed multiple aspects of warfare in ways that persisted long after 1945. Anti-aircraft gunnery evolved from firing thousands of shells per kill to achieving kills with a fraction of the ammunition. Artillery tactics incorporated proximity-fused shells as standard ammunition for anti-personnel missions. Naval doctrine recognized that ships equipped with proximity-fused ammunition could defend themselves against air attack far more effectively than previously possible. And weapons designers understood that sensors and electronics could multiply conventional weapons' effectiveness far beyond what raw explosive power could achieve. The technology itself continued evolving. Post-war proximity fuses used the lessons learned during wartime production to create more reliable, cheaper, and more capable designs. Modern proximity fuses are used in air-to-air missiles, surface-to-air missiles, artillery shells, and various other applications. The principles established by the World War II proximity fuse, using sensors to detect targets and detonate at optimal distance, became fundamental to modern munitions design. Every smart weapon, every guided missile, every sensor-fused munition traces conceptual lineage to the proximity fuse developed in desperation between 1940 and 1942. The strategic impact is harder to quantify, but equally significant. How many ships survived because proximity-fused anti-aircraft fire drove off or destroyed attacking aircraft? How many sailors and soldiers lived because their ships weren't sunk or their positions weren't overrun? How much faster did the war end because German troops couldn't maneuver freely under artillery fire? Because Japanese kamikaze attacks were less effective? Because V-1 attacks failed to make London uninhabitable? These counterfactuals are unanswerable. But the consensus among military historians is that the proximity fuse ranked among the most important technological developments of the war. Comparable to radar, perhaps exceeded only by the atomic bomb, the German failure to develop a functional proximity fuse reflected multiple disadvantages that accumulated into strategic failure. German scientists understood the concept and worked on various designs throughout the war. But they lacked the miniature vacuum tubes that made the American design possible. They lacked the industrial capacity to mass-produce complex electronics while simultaneously producing conventional weapons. They lacked the coordination between scientists, industry, and military that characterized the American program. and by the time German development reached promising stages, the war situation had deteriorated to the point where resources couldn't be spared for unproven technologies. Germany's research was fragmented, underfunded, and ultimately irrelevant because they couldn't bridge the gap between laboratory concept and battlefield weapon. Japan faced similar problems, but more severe. Japanese electronics industry was less sophisticated than Germany's. Japanese research programs were isolated from each other and from production facilities. And Japan's strategic situation meant that even if they developed proximity fuses, manufacturing the millions needed for meaningful impact would have been impossible. The proximity fuse advantage belonged exclusively to the Allies, and that advantage couldn't be countered through anything Japan or Germany could realistically achieve during the war's final years. The billion-dollar secret's legacy. The proximity fuse program cost over $1 billion, roughly equivalent to $15 billion today. At its peak, an estimated 3% of all physicists in the United States worked on proximity fuse development or related research. More than 100 factories participated in manufacturing components and assembling fuses. Hundreds of thousands of workers, many of them women who'd never seen sophisticated electronics before, built the devices by hand under conditions of absolute secrecy. The program rivaled the Manhattan Project in scale and exceeded it in immediate battlefield impact. Yet the proximity fuse received far less public attention than the atomic bomb or radar. The secrecy that protected it during the war persisted into peacetime. The technology was declassified only gradually, and many details remained classified for decades. Unlike the atomic bomb, which announced itself with visible destruction and immediate strategic significance, the proximity fuse worked quietly and incrementally. Each shell that destroyed an aircraft or killed enemy troops was a small victory that accumulated into strategic advantage. There were no dramatic moments, no singular achievements that captured public imagination. Just millions of shells that worked as designed, turning near misses into kills, making Allied forces more effective in ways that were statistically measurable but visually unremarkable. The women who assembled proximity fuses in Ipswich, Massachusetts, and hundreds of other locations across America rarely received recognition for their contributions. They'd worked under intense security, not knowing what they were building, forbidden from discussing their work. After the war, they returned to peacetime lives carrying secrets they still couldn't reveal. Only decades later, when proximity fuse development was declassified and historians began documenting wartime production, did their role become widely known. They'd helped win the war through tedious, eye-straining work that demanded precision and patience. Unglamorous labor that proved as essential as any combat operation. The proximity fuse demonstrated several truths about technological warfare that remained relevant long after World War II ended. First, that small technological advantages, consistently applied, could produce strategic effects exceeding their apparent significance. A device the size of a fist, costing perhaps $20 to manufacture, multiplied artillery and anti-aircraft effectiveness by factors of 3 to 10. Second, that American industrial capacity could manufacture complex technologies at scales that enemies couldn't match even when they understood the principles. Third, that interdisciplinary cooperation between scientists, engineers, manufacturers, and military planners could solve problems that seemed insurmountable when approached individually. Modern warfare's reliance on sensors, electronics, and smart munitions traces directly from the proximity fuse. The concept that weapons could sense their environment and react appropriately rather than simply flying ballistically toward a target, became foundational to modern military technology. Every guided missile, every smart bomb, every sensor-fused artillery shell inherits the proximity fuse's legacy. The principles established between 1940 and 1942 by scientists trying to solve an immediate problem created frameworks that continue guiding weapons development 80 years later. The weapon Hitler never saw coming. Hitler never saw the proximity fuse coming because it represented a form of technological warfare that German military thinking hadn't anticipated. German weapons development emphasized improving existing systems, building better tanks, faster aircraft, more powerful artillery. The proximity fuse represented something different, a fundamental reimagining of how weapons functioned. It took a problem that had existed since anti-aircraft guns were invented. How do you hit a small, fast-moving target? And solved it not through better guns or better aiming, but through sensors that let the weapon itself decide when to detonate. This conceptual leap required trust in electronics and automation that German military culture didn't embrace. German weapons were mechanically sophisticated, but electronically simple. They relied on human operators making decisions and mechanical systems executing them reliably. The proximity fuse inverted this relationship. The human operator just fired the gun, and the electronic system made the critical timing decision. This delegation of decision-making to electronics was conceptually uncomfortable for military organizations accustomed to human control over all weapon functions. The Americans made this leap because they had no alternative. Their anti-aircraft performance in the early war years was abysmal. Standard methods weren't working, and aircraft attacks were killing sailors and soldiers whom conventional anti-aircraft fire couldn't protect. Desperation drove innovation, and the cultural willingness to try unconventional solutions enabled the proximity fuse's development. American scientists proposed an idea that seemed impossible. American industry figured out how to manufacture it, and American military commanders trusted the technology enough to deploy it despite the risks. Hitler never saw it coming, because by the time Germany recognized what the Americans had achieved, it was too late to respond. The proximity fuse appeared in combat in 1943, but Germany didn't fully understand what they were facing until well into 1944. By then, American production was delivering millions of fuses. American forces were using them routinely, and the technological gap was unbridgeable. Germany could research proximity fuses, but they couldn't develop, manufacture, and deploy them before the war ended. The Americans had achieved a technological advantage that couldn't be countered, and that advantage helped ensure the Allied victory. The proximity fuse was the weapon Hitler never saw coming, not because it was secret, though secrecy helped, but because it represented a type of innovation that German military thinking hadn't prepared for. It was small, it was electronic, it was automated, and it worked. In turning near misses into kills, in making artillery and anti-aircraft fire devastatingly more effective, in multiplying the lethality of conventional weapons through sensors and electronics. The proximity fuse previewed the future of warfare. And in that future, the side that could innovate fastest, manufacture at scale, and integrate new technologies into combat operations held decisive advantages that traditional military power couldn't overcome. Thank you for watching and listening. We really appreciate it. Please consider subscribing, liking, and even sharing this video.